Welcome to the session. Greeting of the day. In today's class, we are going to see about plasma arc welding. It is a continuation of the process of tungsten inert gas welding process. We have already seen about various arc welding methods, of SMAW process, submerged arc welding process, and then MIG welding process, and then tungsten inert gas welding process. This all we have already seen. Today we are going to see about the plasma arc welding process. Here also we are going to use a non-consumable electrode of tungsten. This is the same we are going to use here also in the plasma arc welding process. But we are going to generate more plasma for the high melting utilizations that we are going to see. Heat is generated by an electric arc, yes, between the base material and a non-consumable tungsten electrode, or otherwise between the constructed nozzle. It means we are using the non-consumable electrode. That non-consumable electrode connection can be given directly to the workpieces or otherwise to the nozzle also. Two methods of connectivity is there. In this process, the electrode movement can be manual or can be automated control system. Arc and molten weld pool is covered by the inert shielding gas of which one? Can be argon. Inert gases can be helium. That is what inert gases can be argon, helium, neon, krypton. It's not given. Plasma is generated with respect to this ionized gases. What is this? Due to this release of electrons from the electrode, it wants to move towards the downward direction and it is attracted by the ions from the positive end. This formation of ions and electrons causes the ionized gaseous zone in between this arc. That gaseous zones we are calling that as a plasma zone. Hence it is termed as a plasma arc welding process, PAW. Heat is generated by the arc between the base material and the non-consumable tungsten electrode. The plasma arc welding is an advanced version of TIG, what I told you already. Similarly, the PAW with the GTAW, the tungsten electrode and the inert gases of shielding, yes, tungsten electrode we are using as like we are using in the TIG welding. TIG also called as GTAW. Inert gas shielding also like argon. We are using the tungsten electrode, we are using the shielding gas of argon as like a TIG. What is the differences then from the TIG and this one? The differences are the velocity of plasma. We are generating more plasma than that of TIG. That is what I told. Velocity of plasma is different from this TIG and energy density is different from this TIG welding process. These are similarity. These are differences. The large surface area of a TIG welding are exposed to ambient air causes the greater heat losses. So, low thermal efficiency on the TIG. It means the large surface area of TIG are exposed to the air. We are giving double protection here. That is the point. We have an electrode and we have the workpiece. And from this single electrode, we are supplying the shielding gas around it and it is protected. This electrode is come down and it is going to melt and deposit. But what happens here, you see, this single layer of shielding gas protection, ionization is not perfectly made. Ionization are disturbed by this ambient air conditions and fluctuations. Exposure to ambient air fluctuations. Therefore, the thermal conductivity between this air gap is disturbed. This air gap is disturbed in the TIG welding process. Therefore, what I'm doing here, I'm trying to give double the protection now. I'm trying to give double the protection in such a way the plasma ionization can be taken place at the inner layer and the ambient air fluctuations protection atmospheric contamination to be avoided, which will be taken care by the second protection. So that is what I am doing in this setup. You will see. These features affect the penetration. Yes, I am talking about in TIG. In TIG, this ambient air circulation spoils if the heat is not generated, thermal conductivity is spoiled by this air fluctuations. What happens? Penetrations will be spoiled, and then width of the heat affected zones will be spoiled, and then the speed of the welding also will be spoiled. We can't able to move heat, mainly heat needed for melting and depositing. That heat itself, thermal conductivity is spoiled here. Then obviously penetration will not happen, obviously width will not form, obviously welding will be slower. Slowly we have to create more heat. Until then we should wait, and then electrode filler material will be melted, deposited, and we don't know whether it is a full penetration or not, because conductivity is not there. How the full penetration will be found? Solidification will be immediate, fluidity will be less. Such cases, this all problems will be there. Therefore, what I have to do? I have to increase the conductivity, increase the plasma, increase the heat. That we have done through the PAW process. You see, the principle of PAW, inert gas is passed through the inner orifice. There are two zones are there. In these two zones, you see, here there are two zones in this setup. At center, the black color represents the tungsten electrode, as usual, like a TIG process. And then there are two widths are there. There are two cases are there. You should see. See, there are this number one. I am drawing the lines here. So this zone nearer to the electrode, this is one zone where I am giving the plasma shielding, the same tungsten argon we are supplying, but this argon is useful to generate the ionized gas and forms the plasma and forms the heat, and that heat will be utilized for welding. That good thermal conductivity are given by this plasma gas shielding. This gas mixed with the electron flow here, and it comes here. See, this comes down in the center. In the center it comes down. Likewise it comes down, and then it mixed with the electron flow of the electrode, generate heat, and it will be utilized for welding processes. It will be utilized for welding. That is okay. But what's the problem in TIG? These fluctuations are disturbed by the air. That we are avoiding. How we are avoiding? Second layer of protection I am giving. Where I am giving the second layer of protection? I am giving the second layer of protection on the same nozzle at the outer end. See, I am drawing here. See, this is the outer end. This is the outer end. Now I am again supplying the same argon shielding in the outer layer for the protection. So what I am doing? So I am supplying here. This supplying makes the protection, second layer protection, which will be helpful to avoid the air contamination towards the weld center. But in the TIG it happens. But here we are avoiding to the second layer protection of argon shielding gas mixture. So what happens? The first I am calling it as a plasma gas. Second one I am calling it as a shielding gas mixture. At center we have the black color is named as a non-consumable tungsten electrode. So this have the constructed arc, and as usual what we are supplying here? We are supplying here about the direct current, electrode negative. Here the electrode is connected to negative, workpiece connected to positive. Therefore what happens? The electron flow will take place towards the heat, base material. Base material is going to receive the 70% of heat, and 30% will be there. In 30% will be there in the electrode. This 30% of heat in the electrode will be helpful to energize the electrode. Kinetic energy increases, heat increases, releasing of electron. This all will be done by this 30% of heat. But the heat, 70% of heat will be utilized for melting of the filler wire, melting of the base material, but not melting of the non-consumable, because it is 30. It is 70% of heat is at the downward direction. So likewise it can be helpful. That is what? The inert gas passed through the inner orifice, that we know. Now we are using the argon as a plasma gas. Plasma gas. And then inert gas surrounds the tungsten electrode, and subsequently the gas is ionized and conduct electricity. Correct. Now this plasma gas is going to get in contact with the electron flow of the non-consumable electrode. Inert gas surrounds the tungsten electrode, and subsequently gas is ionized and conduct the electricity heat generated. This state of ionized gas is known as plasma. Yes. The plasma arc is allowed to pass through the constructed nozzle, causing high energy and current density. Subsequently, high concentration heat generated with high temperature capable of melting the job. So this center part which is going constructed arc of plasma gas, I am talking about this center one. It having the capability to melt the workpiece. That we can able to do until it is not disturbed with the air contaminations. For that only we are giving the protection of second layer. Low flow rate less than 5 liter is maintained there to avoid the turbulence in the weld pool. Earlier we are told high shielding is needed in the argon when we are talking about the comparison between argon and helium. But here we are giving the double layer protection. Shielding is different. Making the plasma is different. For making the plasma, argon shielding gas to be ionized when the electrons is released from the non-consumable electrode. For that ionization process, it is enough 5 liter per minute is enough, and therefore we are maintaining with the 5 liter per minute important. And therefore, and also by doing this minimum level supplying of the argon plasma gas, we can able to avoid the turbulence in the weld center. Now, this part is over. This flow rate is insufficient for shielding. What happens? If you are supplying the 5 liter per minute, turbulence will not form in the weld pool, that is okay. But atmospheric contaminations will form inside. Therefore, that is to be also protected. Therefore, we are supplying the shielding, argon shielding in the second layer of the nozzle, that we are naming as a shielding gas. How much they are supplying? So, inert gas high flow rate of 30 liters per minute is supplied through the outer nozzle. Through the outer nozzle. Inner nozzle 5 liter per minute. Outer nozzle 30 liter per minute for protection from the atmospheric contamination. Surrounding the inner nozzle to protect the weld pool. Here it is protected for the weld pool. Here this turbulence is avoided on the weld pool. In plasma arc welding, the arc force to pass through the nozzle and cooled copper, which causes the constructed in the arc. The construction of arc reduces the cross section of the area of large. This features makes the high energy density and low heat input welding in the process. So this is setup we should understand clearly. At the center here, at center we have here the plasma arc and the electrode. This setup is over here. And then the outer nozzle, at outer nozzle, this zone. At outer nozzle, we are giving the shielding gas to avoid the atmospheric contaminations. What is the supply of here I am giving? About the polarity, non-consumable electrode we are using. Therefore, direct current, electrode negative I am giving here for the protection, minus and plus 70, 30%. Okay, 70% on base, 30%, 70% on base, 30% on the electrode. And melting and electron flow comes downward direction and it can be welded. So therefore PlasmaArc possesses a few problems associated with the welding, that all other problems are less penetrations, less welding speed, that all can be avoided. So increasing penetrations are done now. Compared to TIG, increased penetrations are done. Reducing the width of the weld bead, because it is a high heat, immediately full pinpoint heating can be done. In the TIG welding itself, pinpoint heating, but this pinpoint heating is further making a keyhole method. Keyhole heating it is made, specific point, and then with this reduced, outside with this reduced, but penetration is increased. We need a complete joining of the material. We no need of increasing of the heat distribution throughout the workpiece. We need joining there. Full penetration we need. We no need of a wider width of the heat zones. Heat affected zones we no need. Therefore it is reduced. Heat HIZ is reduced here. Heat affected zones are reduced. That's the point. Inert gases of argon and helium are frequently used for the protect the molten weld pool. This is usually did in this same as like a TIG welding process. Charged particles of electrons and ions are formed as a result of ionization of plasma gas tends to ruinate the stacking methods. Therefore, we can see the plasma generated due to this arc between the non-consumable electrode and workpiece is called as a transferred plasma arc. Now, I am coming to the classifications of there are in the plasma. It is usually polarity is direct and electronegative, but I am dividing into two categories of non-transferred arc and transferred arc. What is this two? What is this two? You see, I am dividing likewise transferred arc, non-transferred arc. The nozzle, electrode, and then inner plasma, and then likewise. So here also we will put the same. The first one, outer nozzle, the inner one, and then the electrode. So what happens? At the center we are going to supply through red it is a plasma gas. Here also plasma gas, right? And then here we are supplying the shielding gas, where in this location, in the outer zone, it means here, it means here. So how we can, now I can divide these things into two categories of transferred and non-transferred arc. This is I am naming as a transfer, this is I am naming as a non-transferred. How? It means, you see, we have the workpiece here, we have the workpiece here, and then arc to be generated now. In the transferred arc, workpiece is part of the circuit, electrical circuit. It means I am connecting this connection like this. DC, direct current, electrode, negative is given to the non-consumable electrode, and positive connected to the workpiece. Arc is generated here. Directly contact here. It is non-transferred arc. Here what happens? workpiece, not the part of circuit. Arc generated arc between the electrode and nozzle. It means the nozzle is here, yellow color. The arc comes down and arc is generated like this. Arc is generated like this pattern. So what happens? The workpiece can be moved independently. Workpiece can be moved independently. Here how the connections will be? The connections I am connecting here as usual negative, the electrode, and then this nozzle I am connecting as a positive. So the workpiece, the arc generated between these two, the ionization process happened here, the heat happens here. This workpiece also additionally kept between the arc. Therefore, heat only generated is less here. Heat absorbed on the workpiece is less here. Heat absorbed by the workpiece is high here. So we can able to give more heat on the workpiece in the transferred method. More heat is not given in the workpiece in the non-transferred method. The name itself says non-transfer. Arc is not transferred to the work. Here transferred, arc is transferred to the work. So this is the setup we can understand. So what is the application here? Can be keyhole welding. Go for keyhole welding. Go for keyhole welding. So this we can go for thin sheet welding or otherwise simple heat treatment process. Thick welding, thick sheets, thin sheets. Likewise we can keep. Here we can go for thick material. Here we can go for thin material. So like setups we can able to understand from this concepts. So that is what the same I have given. Non-transfer. The arc is established between the electrode and the nozzle. Non-transferred. Now we understand. This is a transfer. The arc is established between the electrode and the workpiece. It is a transferred arc. Now I want to compare this two in the table format. Arc is established between the electrode and the workpiece, non-transferred. Established between electrode and the nozzle. The workpiece is a part of the electrical circuit. Workpiece is a part of the electrical circuit. Workpiece is not the part of the electrical circuit. Heat obtained from the anode spot in plasma jet. Therefore, higher amount of energy is transferred to the work. Higher amount is transferred to the work downwards. Less energy is transmitted to the work setups. Therefore, higher penetration is obtained, so thicker material can be welded. Here, lesser penetration because heat is not there. Heat is directly going to the nozzle. Just we are keeping the workpiece in between. So lesser penetration obtained. So thinner material can be welded here. Higher process efficiency. Higher process here. Less process efficiency are made. So final. For the advantages of plasma arc welding, so welding speeds are higher. Yes, we are giving double protection. We are giving the double protection, double shielding, heat protected. Okay, therefore welding heat, high melting, high deposition. Quickly you can move to the next location. Welding speed is higher. High penetration, same. These are interrelated. This one. High arc stability because we are giving the second layer. Thicker welds, plasma high depth to width ratio because penetration we are concentrating on the pinpoint. So here we can write the pinpoint. Pinpoint control, keyhole. That keyhole welding can do. Keyhole. less distortions by the focused welding, no sparks, no spatters. These are advantages. No fluxes when the consumer electrode is not used. No fluxes, no slag, no smoke, no fumes, nothing is there. All position welding, because the flux falling down, no problem, we can do automatic system. Gas shielding to be given overhead or helium, or instead of argon we can give helium. So all positions welding can be done from 1G to the 6G positions can be done. Low hydrogen, minimum cleaning. Low hydrogen means there is no that rutile fluxes or cellulose fluxes are not there. So hydrogen content is not involved. Maybe from the atmospheric hydrogen involvement will be there, but we are giving the double protection. Therefore, hydrogen also is reduced. But limitations, high radiations are formed, noise during the welding is there, high welder skills are required, are mandatory, high welder skills are important, and then gas consumption is high. Argon we are giving for both for plasma and also for shielding. Therefore, more required than that of the TIG welding process. High equipment running cost, slow travel speed than that of the other process. Even though when you are comparing for the submerged arc welding process, it is slower. Low production rate and high productions are needed. The applications, the weld all materials than that of TIG, piping, tubing, as like a TIG process, as like a TIG also, the reactive materials of titaniums and aluminums can be welded here. Submarine industries, aeronautical industries, jet engines and electronic components are possible. The summary: in welding, we have seen today about the plasma arc welding, in this we have seen about transferred arc and non-transferred arc. Here the contact between electrode and workpiece. Here the contact between electrode and nozzle. Along with that we have seen about advantages and applications. The remaining part of the subjects we will see you in the next session. Thank you.
Plasma arc welding. Plasma arc welding is similar to the tungsten inert gas welding process because it uses the tungsten electrode and argon as the inert shielding gas. The only difference lies in the construction of welding torch. It is based upon the principle that the coalescence of the workpieces is carried out by the heat obtained from the constricted arc between the tungsten electrode and the workpieces. To understand how plasma arc welding process is carried out, let's join these two metal plates using the process. First, let's understand the construction of plasma arc welding. The welding setup consists of a DC generator whose positive terminal is connected to the clamp and the negative terminal is connected to the welding torch. The welding torch basically consists of a non-consumable tungsten electrode surrounded by a constricting nozzle, which is further surrounded by a shielding gas nozzle. Plasma gas passes through the gap between the tungsten electrode and constricting nozzle, and shielding gas passes through the gap between the constricting nozzle and the shielding gas nozzle. The most commonly used plasma and shielding gas is the argon gas. Argon gas is supplied from the argon gas cylinder connected to the welding torch via a DC generator. Now let's use this setup to join these two metal plates. Now let us switch on the power supply and then turn on the knob of the argon gas cylinder. We see that the argon gas flows through the welding torch, and when it comes in contact with the current carrying electrode, it gets ionized. This ionized gas is called plasma. Now when we bring the welding torch closer to the interface of the metal plates, we see that an arc is generated from the welding torch. Note that this arc is called the transferred arc because the generated arc travels from the electrode to the metal plates. This arc remains concentrated and straight due to the squeezing action of the constricting nozzle. This constriction produces a lot of heat at the interface. The plasma gas is also protected by the supply of argon gas through the gap between the constricting nozzle and the shielding gas nozzle. Now, as we move the welding torch and the filler rod along the interfaces of the plates, we see that a thin keyhole gets generated along the interface due to the high temperature of the plasma gas. This keyhole results in the melting of the metal plates along their edges. Now again, when we move the filler rod and the welding torch along the interface of the plates, we see that the melted metal flows back into the keyhole, thus forming a molten joint between the metal plates. Thus, we can say that plasma arc welding is a welding process where the two metal workpieces are joined due to the formation of an arc between the electrode and the workpieces. The arc is basically produced from the plasma gas. Now, let us list the advantages and disadvantages of plasma arc welding. The advantages are as follows. In this process, the heat input can be controlled properly due to its concentration. It offers uniform deep penetration. In this process, the metal deposit rates are higher, and the heat affected zone is small due to the concentration of arc. The disadvantages are as follows. In this process, the welding equipment is expensive, and the nozzle surrounding the electrode needs frequent replacement. Related terms are:
in plasma arc welding, metal coalescence is produced by a constricted arc made up of a high-velocity stream of ionized gas called a plasma. In most plasma arc welding operations, the plasma jet is generated by heating the orifice gas in the torch plenum chamber to a plasma and forcing the plasma to exit through a constricting nozzle or orifice. Partial shielding is obtained from the plasma and is supplemented by an auxiliary shielding gas. Auxiliary shielding gases used include argon, helium, or mixtures of argon with hydrogen or helium. Because of the constricted arc, the heat energy of the plasma stream is concentrated and extremely intense. This permits deep penetration, narrow welds, and rapid welding speeds with good arc stability. Workpieces can be joined with or without filler metal. Plasma arc welding can be used to join most ferrous and non-ferrous metals, including extremely thin materials such as foils. Plasma arc welding equipment cost is high, however, so the process is often limited in its application.